Hi, welcome back to My Smart Learning. It's Mr. Meehan here with your physics lesson, science lesson as well for year 9s. However, this is useful for year 10s and 11s for your GCSE science or physics. What we're looking at today, following last week's work on energy, is specific heat capacity. So last time we talked about conduction, convection, and radiation. The question today I'm looking at is why do some materials get hotter quicker than some and some stay hotter for longer. So some get hot really quick, but some take ages to get hot, but some get hot quickly but then cool down really quickly, and then some stay hot for ages. Why is that? So quick recall PT though, our quick quiz. Number one, what are the three types of heat transfer? So I gave you a clue there, I said them just before. Number two, which happens out of those three in solids? Number three, which happens in fluids? Number four, which can happen through a vacuum? And the last one, number five, what do we call a poor conductor? What do we call poor conductors? Okay, have a quick go at answering those questions and pause the video if you need to, and then if you unpause, we'll go through the answer now. So, three types of heat transfer: conduction, convection, and radiation. Question 2 is infrared radiation. Number 2, which happens in solids? Well, solids has to be conduction because the particles have to be close together. Number 3, which happens in fluids? Fluids are gases or liquids because they flow. That's going to happen, that's going to be your convection. So number 3 is convection. And number 4, which can happen through a vacuum? That one is going to be, because there's no particles, it's going to be radiation, infrared radiation. And number 5, what do we call poor conductors? Well, poor conductors are also known as insulators because they don't conduct. So, specific heat capacity. What does this word actually mean? It's a tricky one. It's quite a hard one to get your head around. So let's break this down. The word specific, if we think about the word specific, it means like a certain thing. Okay, a specific or a unique thing. Heat, obviously we know, is like thermal energy. Okay, so hot objects will have heat. Capacity means how much something can store or hold. So if you imagine a capacity of a beaker, the classic science beaker, that's a 250 milliliters or 250 centimeter cubed. A bottle of Robinson squash, that's like 1 liter, that's its capacity, so 1000 centimeter cubed. So capacity is how much something can hold, whether it be a fluid like the volume, or it could be the amount of energy that is stored in it. So definition, what is it? The amount of thermal energy a material can store is what its specific heat capacity is. But what does it depend on, and why do we call it specific? Well, it depends on the material itself, so the mass of that material as well. And why do we call it specific? Because each material is unique, because each substance is made from different types of atoms. Each material will have its own unique specific heat capacity. But the definition is something you need to learn and memorize. So can you make sure as part of your learning for this lesson is you learn the definition for specific heat capacity, and it's this. Specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degrees Celsius. So it's the amount of energy, or the specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So there's two number ones in there. You have to remember 1 kg and 1 degree Celsius. But that's very academic language. What does that mean in normal language? Well, imagine I have a litre of water. Now a litre of water is 1 kilogram. Okay, so it's 1000 centimeter cube. A kilogram of water will weigh exactly 1 kilogram if it's pure water. And if I was going to heat it up, so if it's at room temperature, if I just got a litre of water in a jug and I was going to heat it up just by 1 degree Celsius, I'd have to put in 4,200 joules of energy just to raise its temperature by 1 degree Celsius. So water has a specific heat capacity. It's how much energy does it need? And every substance has its own unique number. So we'll come back to a few examples in a second. But the formula then, guys, you have to memorize this one. Energy then is mass times the specific heat capacity times the temperature change. Remember, the energy is measured in joules, the mass is in kilograms, The specific heat capacity is joules per kilogram degree Celsius, and the temperature is in degrees Celsius. Now again, you can put this into a triangle. If you imagine I put it into a triangle and I put the E at the top, because that's the energy, it's those three things timed together. Now we use a symbol theta, which I'll show you in a minute, which is a circle with a line through it. It's just a Greek letter to represent the temperature change. So that's the formula, mc theta we call it. We use the letter M for mass, we use the letter C, a little c for specific heat capacity, and we use the letter, it's a theta, which I'll show you in a minute, to represent the temperature change. So we say E equals mc theta. So that's the one you have to learn for today's lesson. E equals mc theta. So it looks like that then. So energy transferred. Now the energy transfer, it's got this little triangle, this funny triangle here. It's a capital letter in the Greek alphabet and it represents the letter delta. So if you know a little bit about the Greek alphabet, you get like alpha, beta, gamma, delta, and so on, just like ours, A, B, C, D. But that little triangle represents the Greek letter delta, and in maths and science we use it to represent the change in something. So something's changed. It started from the beginning and it's gone to the end. So the difference in the change from the beginning to the end. So the change in energy is the mass times specific heat capacity times the temperature change. And again, you can see you've got this little triangle, delta, theta. This little symbol here, the little circle with a line going through it, is another Greek letter called theta, and it's just the symbol we represent the temperature by. And then the triangle there to represent the change in the delta theta, the change in the temperature. So that's the formula, E equals mc theta. But if you want to rearrange that to work out the specific heat capacity, I'll put the mass and the theta together and I'll shift them underneath the energy, just like that. So there's the energy, and I'll put the mass and the theta underneath it. So the specific heat capacity is the energy divided by mass times theta. So that's the formula. That's why it becomes joules per kilograms degrees Celsius. They go underneath. It's just a bit of algebra there just to rearrange it. Now, foundation paper, all you need to do is memorize it and just stick the numbers in. Higher paper though, you'd have to be able to rearrange that formula to get that and then plug in the numbers, okay, in substitution. But it's just some straightforward algebra. Now, let's just talk about what this actually means then. So specific heat capacity is the amount of energy you need to make something's temperature go up by 1 degree Celsius. But that something has to be exactly 1 kilogram. So if I get a kilogram of water and I want to warm it up just by 1 degree Celsius, I need to stick in there 4,200 joules worth of energy. Now, here's the thing. 4,200 joules of energy is a lot of energy. Water's got a very high specific heat capacity because water, it's very hard to get it hot. So if you think about heating up water when you're cooking pasta on your cooker or rice or anything like that, if you imagine you get that pot and you put it on the fire, on the gas ring in your cooker, or it could be electric. Now if you imagine I fill it up with water, so there's loads of water in there, and I switch it on and I leave it for 10, 20, 30 seconds or so, and I go back and tap my finger, put my finger into the water, does it feel hot or does it feel maybe tepid or lukewarm or still cold? And what about the metal of the saucepan after 10, 20, 30 seconds? Now obviously you would never go and obviously put your hands on that metal because you'd burn your hands, because the metal is a very good conductor. It gets hot very quickly. This comes back to our learning objective. Why do things get hot quickly? Well, metals are extremely good conductors because they've got delocalized electrons, the atoms vibrate and they send the energy, thermal energy through easily. They're good conductors. But on the flip side, they have low specific heat capacity, because if you think about it like this, so water, if I put my finger in that water takes ages to get hot. So even after about a minute or so, the water might be only just about lukewarm or just getting a bit hot. It's not getting hot at all very quickly at all, because the amount of energy you need to put into that water is so much, 4,200 for every 1 degrees. So if you've got tap water in your pot, which is 20 degrees, and you're trying to get it to boil 100 degrees, you need to raise it by 80 degrees Celsius. To get to that temperature, you need to put thousands and thousands and thousands of joules of energy into it just to get it to boil. Hence why when you're making some tea, you've got the kettle on. Now if you're making it just for yourself, you shouldn't fill up the whole kettle because you're wasting energy. Your electric bill is going towards heating that kettle up. If you've got a full kettle and it's just you having that tea and you only need this much water and you fill it up to this much, you've just heated all that water up, and the amount of energy you've had to put in there, you just waste that energy because you're just going to let it just cool down and the heat just going to dissipate into the surroundings. Unless you're making for the whole household, if you're going to fill up the kettle, if you're just making for yourself, just that much, because water's specific heat capacity, and here's another number you need to recognize and memorize, is 4,200 or 4.2 kilojoules. So 4.2 kilojoules or 4,200 joules per kilogram degrees Celsius is water's specific heat capacity, and that's the only one you have to memorize. The rest of the other guys you don't need to, because water's the one you always come across. The others you'll get information based on it, where you have to do the calculation. So that's what specific heat capacity is. If I put my finger in that water, it doesn't get hot very quick, but then when I switch off the pan, if you imagine I pour that water into a cup, like for your tea or whatever, that tea will stay hot for a good 15-20 minutes. It'll stay hot. You put your finger in it, after a few minutes it still stays hot because it retains that heat energy in that water, because it's got very high specific heat capacity. You put all of that energy into that water and it stores it very well. Obviously over time it dissipates and spreads out into the environment. However, with the metal though, if you think about it, you put your hands on the pan, you'll burn your hands straight away because it gets hot very, very quickly. But if you leave the pan, take all the water out, and you've just left the pan there on the cooker, and you switch the cooker off, and you come back to it after a minute and put your hand on it, it's only going to feel a little bit warm. And after a couple of minutes, it's gone cold again. Metals have very low specific heat capacity. Here's the thing, a question to think about. Why do we use oil to cook rather than, let's say, water? Well, oil specific heat capacity is a lot less than water, but oil doesn't boil, that rhymes, oil doesn't boil at 100 degrees Celsius, whereas water does. So when you cook with water and you're boiling it, you can only cook something to 100 degrees Celsius. So the textures and the flavors of the food will taste different and feel different in your mouth when you boil something compared to if you fry something. Because if you fry something, the oil can go up to 300 degrees Celsius before it won't boil. So obviously when you put potatoes in water, it gets soft. Boiled potatoes could become like mashed potato, so they're white all the way through. Whereas if you fry it, it becomes chips. Why? The inside's white and fluffy, but the outside's crispy because it's cooked the outside to a higher temperature than the inside. So the texture and the taste is different. So that's just something to think about. So why use water in boilers then? So look at the specific heat capacity of water, 4,200. And then the lead and so on and so on. So water's got very high specific heat capacity, so you can heat it. It takes a lot of energy to heat it up, but once that energy is in there, you can transfer that energy around your house for your home to be warmed up. So specific heat capacity then, it's our definition that we just talked about, but look at copper's specific heat capacity. Water's 4,200, memorize that number. Look at copper, you don't need to memorize this one, it's 390 joules, a lot less. Okay, so metals have a lot lower specific heat capacity. Here's your formula again, E equals mc theta, and the E represents the energy in joules, the mass is in kilograms. We must make sure you convert the mass into kilograms. So if the question says 500 grams, you need to convert it into 0.5 kilograms. And you've also got your specific heat capacity, which is in joules per kilogram degrees Celsius, and the temperature change is in degrees Celsius. So here's a question for you. Have a go at this, pause the video and see if you can calculate the answer to this. Okay, now if you've had a go, then you should remember energy is mass times specific heat capacity times the temperature change. Well, the mass, remember if it's 600 grams, it needs to be converted into kilograms, which is 0.6, times the specific heat capacity of water, which is 4,200, you put that in there. Temperature change, it's gone up by 80 degrees. So I need to put those numbers in, 0.6 times 4,200 times 80, and voila, that's your answer, 201,600 joules. Now you could convert that into kilojoules by dividing by 1,000, so that becomes 201.6 kilojoules. Straightforward as that. So that's the first aspect of this lesson, is calculating the energy needed or the specific heat capacity based on this formula, and the definition of what specific heat capacity is. We'll have a go at a few examples, and then we're going to go on to the required practical, which is the tricky, the hard bit of this particular lesson. So what about this question? Water specific heat capacity is 4,200 joules per kilogram. How much energy is required to heat 2 kilograms of water from 10 to 100? So here we've got the mass, which is 2, so that goes there. we've got the specific heat capacity 4,200, which goes there. It's the temperature change we need. It's gone from 10 to 100, so it's 100 take away 10, that makes that one 90. So have a go at that question, and if you've done that, here is your answer. Okay, so 2 times 4,200 times 90 gives us 756,000 joules of energy. What about this one? Pause the video, have a go at this one. And if you've had a go, so again, we've got our numbers. The mass is 4, that goes there. Specific heat capacity we know is 4,200, that goes there. The temperature change though has gone from 10 to 20, so the temperature change is 20 take away 10, which is 10. And therefore, there's your answer. 4 times 4,200 times 10 gives us 168,000 joules. Simple so far? Okay, have a go at these questions. Okay, practice them. It's exactly the same thing. So you got the following materials. So you got this material here, water we've already got. So you've done that calculation already. But try for oil, aluminium. Now look at these numbers. Look at these. Metals got much lower specific heat capacities compared to water, because these guys get hot very quickly, but they cool down very quickly because you haven't put that much energy into them. The temperature rises extremely sharply because they've got very low specific heat capacities. That's why their temperatures rise so quickly by just putting a little bit of energy into them. Whereas this guy, you need to put a lot of energy into it just to get its temperature to rise. But once it's in there, it'll stay in there for longer and it'll dissipate the energy more slowly. Okay? So that's the reason for it. What you need to do then with these numbers is you got the mass, the 2 for each of them. You got the temperature change, which is 10 degrees Celsius. So what you're going to do is 2 times the number times the 10, and it'll give you the answer to each of those. Okay, so have a go at those just to get some practice using that formula, E equals mc theta. Now, what's this? This is something called a storage heater. Now, what do I mean by a storage heater? Now, back in the day, old school now, we've all got, most of us got central heating in our homes. Some of us have electric heaters, some of us have gas fires and what have you in the house. But generally speaking, most of us use central heating systems where the water gets heated in the boiler, the hot water then gets pumped around the house to the radiators, and then the radiators warm up our rooms. That's using gas fires. Now, some houses don't have gas, especially in big high-rise towers and stuff. They're not allowed to use gas, so they have to use electric. Now, the electric board, they have to make electricity 24/7, but different times of the day, most people don't use electricity. Well, when's that? Well, middle of the night when you're asleep, the power station's still running, making electricity, and if you don't use it while it's being made, that's a waste because it has to get made. It doesn't get stored like in a battery. It's constantly being used. So what they try to do is they try to lower the price in the night time, in the evenings, well, like, you know, after midnight, just so that more people are more likely to use it when it's at a cheaper rate. So they use these things called Economy 7. These are little storage heaters. So the way these guys work is you've got inside of them these concrete blocks. Now concrete, we can have a look at concrete. I think it was there. 850 joules of energy you need to heat up 1 kilogram 1 degree Celsius. It's got a fairly lowish specific heat capacity compared to water, but what you do is got electric wires running through them, but they don't heat up during the day. What happens is at night time when we're all asleep, so they say from midnight till 6 AM, what will happen is the electric wires will heat up because the current will go through them, warming those concrete blocks up. So the concrete blocks get gradually quite hot. But then what will happen during the day, the electric will switch off because it's cheaper during the night than it is during the day. So then you're not wasting the cost of the electricity is going to be higher during the day, so then it's switched off obviously. The concrete blocks then will dissipate their heat slowly throughout the whole day. So during the day when we're out up and about doing stuff, it's gradually warming the room up at a cheaper price than if you did it during the day. And that's how these storage heaters work. And sometimes they have like a little fan in there just to dissipate that heat as well, just to blow the warm air out. But generally speaking, it's just a concrete block in there with electric wires running around them, just warming those concrete blocks up, because when you put electric current through a wire, the wire gets hotter. Now, the hard bit, the really, really hard bit. Okay, there's a required practical that you have to do with this investigation, investigate a specific heat capacity. There's 2 ways of doing it. This bit here is the same. You've got this metal block, Now here's an aluminium block. It could be aluminium, it could be copper, it could be steel, whichever block. The block is made so that the size of it is exactly, or the mass of it is exactly 1 kilogram. So therefore you don't need to use the mass number in there because it's 1, okay? So, but what you've got is an electric heater. This electric heater then, as you put current through it, it warms up this electric heater, therefore it warms up the block. And there's a thermometer that sits snugly in a little slot in the metal block, and you can measure the temperature of it. And this block is covered, it's surrounded by a foam or some kind of cloth as insulation to reduce any heat loss, because if you're heating it up there'll be heat losses as it dissipates to its surroundings. So you can see it's completely surrounded and covered to reduce any heat losses, because you're warming it up and you're trying to take an accurate temperature reading. Now you can take a temperature reading. You can either use a piece of equipment called a joule meter, which will actually give you the actual energy that is going into that heater. So the joule meter does it for you. That's like a cheap method really, because it gives you the energy for you. Now in our school, and most schools, we don't have joule meters, but what we do have is we have a power pack. Okay, that's that 12-volt power pack there. You've got an ammeter to measure the current, and you've got a voltmeter to measure the potential difference of the voltage. And obviously you've got a stopwatch to measure time. And using those 3 numbers, we can actually calculate the energy. So that machine just does it for you. So it makes your life a lot easier, because it's just a computer. It's a machine that calculates the actual energy transferred into that heater. Whereas in our school, we're going to have to do old school, we have to actually calculate it. So this is how it's set up. The mass will always be 1 kilogram, because we've got them uniquely made already, that they're already 1 kilogram. But you need to calculate the work done. Remember, work done is energy transferred by the heater into the block. And then you're going to plot the temperature versus the work done. And that gradient will give us the specific heat capacity of that piece of material, that substance. Okay? So you're going to connect the equipment up as follows, like we said. You got you could put it on a 12 volts. You can put it at whatever voltage you want, but 12 volts is fine. But you got to make sure that you keep it at the same voltage the entire time. You don't flip it around or switch it around to give it different voltages. And what will happen is the electric heater will start to get hot, and the heat will spread from that heater into the metal block. The thermometer then will pick up how hot this metal block is getting. Okay? So it says wait 2 minutes to allow the thermometer to start reading a temperature, because if you start measuring straight away, the temperature kind of stays steady and flat for a little while the heating effect happens, until the temperature rise starts to go up. That's why it says leave it for a couple of minutes. Then every 60 seconds you take the temperature as well as the voltage, the current, and the time. Okay? And you're going to be recording that then. So you're going to record the voltage, you're going to record the current, and you're going to record the time. And you're going to calculate the energy by multiplying those 3 things together. That's how you calculate the energy. You're going to take the temperature by the thermometer. That's the temperature that you're measuring. The mass is 1, because those blocks that we've got already set at 1. But if you're in a school where you don't have it set at 1, you have to give the mass as well in kilograms. And then doing the gradient of the graph that you'll see in a second will give us the specific heat capacity. So a results table could look like this. So every 60 seconds, you write down what the voltage is, what the current is, we've got the time. If you multiply those 3 numbers together, we'll give you the energy transfer. And then you record the temperature. Now here's some results from a lesson that we did a few weeks ago. Okay, so I've set it at 12 volts and it stayed exactly at 12 volts. The current stayed exactly the same as well, because I didn't amend that, I didn't change that. I just set it up and I just start the stopwatch. And after those many seconds, you multiply them out and you can see these were in kilojoules, because this was 1,500, that was 3,000, 4,500. You can see the temperature, the energy transferred, or the work done into that metal block. And that was the temperature change. You can see the metal block, at first it didn't go up at all, but then it started to go up by the same amount every time pretty much. Okay, so you end up with your results. You need to get the energy, you do the current times time times the voltage. Okay, you multiply those 3 numbers together, because E equals mc theta. What do I work out? So how do I work out C? Well, remember, to get the energy, it's what we call, I remember like this, you'll learn more about it when you do your electricity topic, but the current letter is I, time is T, the voltage is V, I remember as ITV, like the TV channel. So E equals ITV. Energy E equals MC theta. So here is another set of results. E equals ITV. The specific heat capacity then is the energy divided by the change in temperature. Remember, that's what we did. So if I plot a graph then, if I get, here's some more results. Okay, so if I plot a graph of my work done against my temperature, so I've got these numbers on the x-axis, my energy, and then this is my temperature on my y-axis. Okay, so you plot a graph, so your work done is on the x-axis, your y-axis is your temperature, you draw a line of best fit, and then you can calculate the gradient of that line. So the line will go up, and to work out the gradient, you work out the change in y over the change in x, and that will calculate the specific heat capacity. But the problem is that gradient is going to be the temperature divided by the energy, but we want it the other way around. So you need to get the answer to that, once you've got the gradient, you do the inverse of that, you do 1 over the gradient, and that will actually give us the specific heat capacity. What does this all mean? This all sounds very confusing. It is complicated, especially for year 9, if you do this in year 9. It's even complicated for year 10 and 11, and even A-level students. But ultimately what you've got is we've calculated the energy by doing E equals ITV, the current times the voltage times the time. And that goes along there. Then what we've done is we've measured the temperature by looking at the thermometer. That number goes up along there. So you just measure it and it goes up, 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 up. And I want to measure, now this is sort of GCSE math now, you want to measure the gradient of that line. So it's the change in y over the change in x. Okay? If you're not sure about how to do gradients, we'll come back to that. We'll have a go at that when we're in class. But you ultimately get the gradient. The problem with that gradient is it's that divided by that. But the specific heat capacity is the other way around. It's this divided by this. So when you calculate the gradient, you need to flip it round upside down. So we need to do 1 over the C, specific heat capacity. So all you need to do is just the inverse of the answer to the gradient, and that gives us our specific heat capacity. Here's some key words, the key points there, and some questions for you guys to have a go at, exam style questions. Hopefully you've learned something today. It is quite a tricky one, quite complex, but have a go. Use your computer book and your bite-sized pages that I'll put and show my homework. Hopefully this has been useful for you and you learned something today. And I hope you're keeping safe your night. And I'll see you guys next time when we look at heating homes. Hope that's been helpful, and I'll see you next time. And I forgot to give you your virtual high five, because remember, you can't buy those in the shop. High five.